Hello everyone and welcome to our next revision lesson on P7. Today we are going to be looking at transferring energy. Again, there is a fill in the gaps sheet that goes alongside this, which is optional, so if you find that useful, please feel free to use it. We'll be pausing the video at various points to do practice questions. These are obviously just rough work, so you can do them wherever you want. So first thing is electrical appliances. Electrical appliances, no real surprise, transfer energy electrically. They always transfer it from a chemical store, e.g. a battery, to a thermal store because the wire gets hot. So every time you have an electrical appliance, it may have different outputs as well, but please make sure you always have that thermal store. Even if the electrical appliance doesn't use a battery, it still starts at the chemical because we assume that most energy that we are using comes from power plants that burn things and release energy from their chemical store. So always include the chemical store and the thermal store. Now, I'm sure you probably hated these when we did these the first time round. These are diagrams which are meant to show what type of energy started in a situation, how it's transferred, and what type of energy store we end up in. So please don't think that these are overly complicated. You just need to think where are we starting, where's the energy, how is it transferred, where are we ending, where's the energy then? So here I've got an example, using a toaster. You can see that this table is split into two rows. The top row is a physical situation. Now they are probably going to give you the physical situation and then get you to do the energy analysis underneath. So physical situation here, bread in toaster, not switched on. Transfer, a current flows, heating up the element in the toaster, and the end, the bread is toasted. So looking at the energy analysis, this is a bit interesting. I've drawn two boxes, and these are meant to represent basically the energy stores. I think it is a completely naff way of doing this. However, this is how the textbook has presented these energy analysis diagrams. So that's obviously what I'm teaching you. But it frustrates me that they're not accurate. So please don't worry about how high chemical potential should be and how low it should be, in terms of millimetres and centimetres. Just show the fact that it's got smaller and that the thermal has got larger. That's all you need to do. It doesn't need to be accurate. So yes, you can see at the beginning, you've got a high store of chemical because that is in the power plant or power station that's creating our electricity, and there's a low thermal store. The transfer, we've already talked about the fact that whenever you use something electrical, you're transferring electricity and heating through radiation. And then at the end, you can see there's less in the chemical store and more in the thermal. So as I say, please don't overcomplicate it. It's not too hard. Just think logically. So now, we'll ignore that. Energy always transfers from a hot object to a cold object. Now, I'm trying to think of an example. You've got a hot cup of tea and you leave it on the side. What happens? It becomes colder. But the energy doesn't just disappear. What's happened is that the energy from your cup of tea has been used to heat up the surroundings. The air around your cup was colder, so it's now got hotter because it's had energy transferred to it. Yes, you can increase energy in a thermal store by either burning a fuel to using an electric current to transfer energy from a fuel. You can obviously also leave hot objects around, but these are the easiest ways of looking at it. Now, if you did the placemat last lesson, you would have seen a bit on thermal conductivity. Obviously, when I'm giving you revision here, although I may not have talked about it in the video, the revision resources always cover the entire topic, so you may get a bit of crossover. So thermal conductivity tells you how quickly energy is transferred through a material with an area 1 metre squared, thickness of 1 metre, and temperature difference across it of 1 degree C. The higher the thermal conductivity, the less insulating the material, and the faster energy will transfer across it. Ice actually, bizarrely, has a low thermal conductivity, and so even igloos can be warm. So when you are building a house, if you are looking to go into architecture, for example, you need to consider the thermal conductivity of different materials. What type of material are you going to be using for the walls? What's the thermal conductivity? How energy efficient is that house going to be? Interestingly, with the ice, fish are able to live in a frozen lake because the top layer of the lake will often freeze and provide almost an insulating layer. so that the water underneath stays at an ambient temperature and fish are able to live in there because of that, as I say, low thermal conductivity of ice. So yeah, kind of odd. Efficiency. Again, something that popped up in the board sheet last lesson, tells us how much of the input energy is converted to the useful output rather than wasted. No appliance is 100% efficient. Some energy is always dissipated to the surroundings. And again, we'll go into dissipation later on today. So there is an equation. Efficiency is useful output power or energy over total input power or energy. Now, I, in the board sheet, just wrote useful over total. Okay, that's how I remember it. But obviously, it can be power or energy. Just be aware of that. So I've got an example here. Filament light bulb, 100 joules of energy. Sorry, apologies. Shouldn't be chemical. Sorry, it shouldn't be electrical. Yes, I'm trying to write on you. Oh, my pen's run out. Shouldn't be electrical, that should be chemical. Hang on, apologies. Just plugging in my Apple Pencil to charge. There you go, right, it's charging. Goes to 9 joules of light and 91 joules of heat. Therefore, a filament light bulb is 0.09 or 9% efficient. Either is fine in terms of writing it. I would tend to put things without bothering to put them as percentages, but if you prefer percentages, you can write them. So, have a go at some of these. Pause the video and then I shall go through the answers. Okay, question 1a. A petrol engine that transforms 1000 joules of chemical energy into 300 joules of kinetic energy and 700 joules of wasted thermal. So, it's a bit big, isn't it? Hang on. Efficiency equals useful over total, which is 300 joules, because the kinetic energy is what you actually want from an engine, over 1000, giving you 0.3, or 30%. But as I say, I'm just leaving mine as a decimal. Because it's just a ratio, it doesn't have a unit. B, an electric motor that transforms 1000 joules of chemical energy into 975 joules of kinetic energy and 25 joules of wasted thermal. So useful over total, 975 over 1000 gives you 0.975. C, a solar cell that transforms 300 joules of thermal energy into 45 joules of chemical and 255 joules of wasted. So useful over total. The useful is that 45 divided by what goes in, 300, gives you 0.15. D, a wind turbine that transforms 500 joules of kinetic energy in the wind to 150 joules of chemical energy and 350 joules of wasted thermal. So E is useful over total. 150 over 500 equals 0.3. 2a, what would the total input energy have to be for the following? A light bulb that is 50% efficient and transfers 40 joules of light. So total is going to be useful over efficiency. 40 over 0.5 gives me 80 joules. A light bulb that is 90% efficient transfers 40 joules of light. Useful over efficiency. 40 over 0.9. I'm going to have to do that one in my calculator, but I imagine it's going to come out as, what have we got? 44.4, there we go. And again, that's in joules. Okay, we're nearly done. Energy dissipation. When energy transfers to the surroundings, we say it dissipates. This means it is too spread out to be useful. We can reduce energy dissipation by reducing friction or thermal conductivity, using a lubricant, for example, or wrapping something in insulation. Now, we do have to pay for electricity. Every home, yours included, will contain an electricity meter that measures the number of kilowatt hours of energy that a household uses. 1 kilowatt hour is a unit of energy, defined as the energy transferred by a device with a power of 1 kilowatt operating for a time of 1 hour. Just a quick note, we use kilowatt hours because 1 kilowatt hour is equivalent to 3.6 megajoules, or 3.6 million joules. If we were to pay for electricity in joules, we'd be looking in millions, and that's just pain. So they put it in kilowatt hours because it's a much bigger unit, so that the numbers are much easier to deal with. So you still use the same equation, energy, power, time. However, please notice power is now measured in kilowatts and time is measured in hours. The total cost is going to be the cost per kilowatt hour times the number of kilowatts. Times the number of kilowatt hours. So again, if you can please pause the video and have a go at these questions, and I shall go through the answers. Okay, so assuming everyone's had a go, question 1A. 4 kilowatt television is on for 1 hour. How much energy in kilowatt hours does it use? Energy is power times time. 4 times 1 is 4 kilowatt hours. B. If each kilowatt hour costs 5p, how much does the TV cost to run? 4 kilowatt hours times 5p each gives you a total cost of 20p. 2. A 2 kilowatt Xbox is on for 3 hours over a week. How much energy does it use? Energy is power times time. 2 times 3 equals 6 kilowatt hours. Each one costs 7p. How much does it cost to run for the week? 6 times 7 equals 42p. 3A. From looking at the pictures, write down the amount of kilowatt hours used. So all you need to do is take one away from the other, and I think that works out as 87 kilowatt hours. Calculate how much the cost of electricity was if the price of 1 kilowatt hour is 12p. So you just do 87 times 12p, giving you an answer of 1044p or £10.44. And that's it. Thanks everyone.